series of positive terms. As the name, as the heading explains you, we are going to consider a series in which all the terms are positive. It's a regular way of expecting it, right? But still, you see, you can look at these words here. An infinite series in which all the terms after some particular terms are positive is a positive term series. Understand, look at this example, you will understand it. Looking at this example, you see I've written about 3 plus 3, 7 terms in this series. If you look at this carefully, there are first 3 terms, you see them? First 3 terms here are actually negative. But after this third term, remaining all are completely positive only, right? So here, even if certain number of terms are negative, this statement says, even if there are few terms which are negative, still I can consider, remember this, there are only few terms which are negative, but except them, remaining all are definitely positive only. In such a case, I'm also considering this series as what you call a positive term series. The idea here is, you see, a few minutes ago, we have discussed about one property. If you add or remove certain finite number of terms from a series, that should not influence the convergence or divergence of the series, isn't it? So here, if you just ignore these 3 terms, so ignorance of these 3 terms should not really affect convergence or divergence of this series, isn't it? If the remaining terms together, if you only consider the remaining portion here, if you consider only this portion, remaining terms, if that series is convergent, then automatically, even if you include those 3 terms, that will be convergent only, right? So whatever the methods we are going to discuss from now, if it is for only positive terms, yes, even if you consider only these positive terms, and if that is a convergent series, definitely, even if you include these three terms, it will also be a convergent series only. So since the influence of very finite number of negative terms has no influence, I can ignore these negative terms and I can consider this series as also a positive term series, in simple to say, right? That's how what you are saying here, you see, an infinite series in which all the terms after some particular terms. Here you see there are 3 terms which are negative, but after these 3 terms, remaining all are positive only. In such a case, we can call this as what you call a positive term series, right? So loosely speaking, I can say this as a positive series, but mathematically, I can take it as a series where each term is positive, right? So to say definition, to define it a proper way, we'll just write it like this, where each un is greater than 0, then only we call it as a positive series. But in practice, even if you have some finite number of terms in that series, we'll still take it as positive term series only. If you look at, if you recall what you call this Fibonacci series, I hope you remember the Fibonacci sequence. What it starts, where it starts with 1, 1, 1, 2, then 1 plus 2, 3, then 2 plus 3, 5, then 3 plus 5, 8. Then you see what you have 5 plus 8, 13, and so on. You can write as many words as you can write. So if you can add, these are all numbers from a sequence, as you know. If you add all these terms, that's going to be a series. So what will be the series here in this case? It is 1 plus 1 plus 2 plus 3. You can write like this, you see. If you add all these terms, it's going to be a series. Fine. But see, if you look at these terms here, there is a small thing. The first term and the second term, will choose them as we like. But from second, third term onwards, you can easily expect, you see, there is a specific rule here. From third term onwards, if you add its corresponding previous 2 terms, we'll get the third term. Right? Like that, if you want to get this fourth time, we need to add second and third. To get what you call this fifth term here, we must add third and fourth. So like this, if you want to get nth term in this sequence, or else nth term in this series, you need to add its corresponding previous 2 values, un-1 and un-2. Then you will get what you call the nth term, let us say un, right? But see, what about these 2 terms here? How can we get these 2? Can't we take them as some members of this series? Though they are members of the series, these 2 have no special influence. If you just ignore them also, the convergence of the series remains the same. right? We are just selecting them as we like, you know. That's how you see, understand, there are many series where we need to ignore some of the terms from the series, right? In order to verify the convergence of a series, we definitely have to ignore some of the terms, right? That is only we are discussing to define what you call series of positive terms, even though there are few negative terms, very finite number of negative terms, then also you can consider it as a positive term series only, right? So that is the major story here. But before getting into, now the question is actually, when you are given a positive term series, how to verify whether that series is convergent or not, how to test whether that series is convergent or not. Okay, I'll come to that, but before that, let me tell you what happens when it is convergent. Okay, right? The question is surely how to verify whether it is convergent or not. But before that, I'm just trying to tell you what happens when the given positive term series is convergent. As you can see here, if the series of positive terms, let us say summation un, right? If the series of positive summation un is convergent, if it is convergent, then we say limit n tends to infinity un, limit n tends to infinity un is directly, I mean, you know, always this is equal to what you call 0, right? When you are given a series of positive terms which is convergent, understand it is already convergent. When it is already convergent, then certainly for nth term, if you calculate the limit, it will be definitely equal to 0, right? Now, see, this is only a necessary condition for convergence of the series, right? What do you mean by necessary condition? Understand it this way. I can say this is a unidirectional statement. I mean, if un is convergent, then automatically limit will be equal to 0. But if the limit is equals to 0, corresponding to that, you see, series may not be convergent, right? When the series is convergent, certainly limit will be 0, but it may not be true from the other side, right? So that's how I'm saying it is only a necessary condition, unidirectional statement. It follows only in one direction, but it's not true in the other direction. Okay, but anyway, let me just try to prove this. Let me just explain you the proof of this, how the limit will be equal to 0. Looking at this, understand what you are given here. You are simply given the series un is convergent. Understand how you are verifying actually whether the series is convergent or not. To verify whether this is convergent or not, we are always defining a sequence of what you call uh, partial sums, isn't it? We are just defining a sequence of partial sums, and see what it is actually. Sn is, if you just add first n terms of the series, it is this, you see, u1 plus u2 plus and so on un, right? So this is the sum of first n terms from the series. So we are taking this as Sn. Now, to verify whether the given series is convergent or not, right, whatever the series it is, we are just calculating the limit of this Sn as n tends to infinity. If this is a finite value, then we are saying the series is convergent. And if this is an infinite value or limit doesn't exist, in that case, we are saying this series is what you call a divergent series. Understand, here you are given already this series is a convergent series, right? So what must have happened already when it is a convergent series? Definitely there must be a sequence of partial sums, and even for that there must be a limit whose value is which has a finite value. So let us say if that finite value is L, right? Since you are given the series is convergent, there is a sequence Sn. Sn is sum of first n terms of this series, and it is such that, you know, limit n tends to Sn is a finite value. Let us say that finite value is L. So the same thing has, you know, we have considered here. You have just defined Sn. Sn is the sum of first n terms in the series. Understand, when Sn is sum of first n terms, what will be Sn minus 1, right? Here we need to take sum of first n minus 1 terms. Look at this. We need to take sum of first n minus 1 terms, right? So this is Sn minus 1. If you majorly observe the difference between these two, what you have extra in Sn, up to un minus 1, both are same. But in Sn, there is one term extra, which is un. That's how you can see When you take the difference between these two, Sn minus 1, we'll get it as Un, right? Now, stay there. Let me just add one more point here. You are given already the series Un is convergent. When you are given this summation Un is convergent, we have defined a sequence Sn, and even it is also convergent because we got the limit as a finite value. Understand, actually, if you write all the terms, they'll be like this: terms of sequence S1, S2, and so on, Sn minus 1, comma Sn. Understand here, Sn and Sn minus 1, these two are successive terms. Sn minus 1 is a term just prior to what you call Sn. That's how when n tends to infinity, if Sn approaches to L, because these two are just successive terms, as n tends to infinity, even Sn minus 1 also approach to L only, because they are just successive terms, right? Because we are discussing about the limit. After some kth term, if you recall the limit of a sequence, after some kth term, all the remaining terms will be in a neighborhood of L. Not only Sn or Sn minus 1, even few other terms will also be in the neighborhood of L only. That's how even for Sn minus 1, the limit will be L only, right? So keeping this idea also in mind, I'm just continuing like this. You see, the question is to calculate the value of this limit. So I'm just considering, the left-hand side part here. Limit n tends to infinity Un. Now, when I consider this, I can replace, this portion Un by this expression. So I have replaced Un by Sn minus Sn minus 1. But you see, as we know, when you take limit, limit of a minus b, we can write it as, limit a minus limit b. You see, taking this idea, I'm writing it as limit n tends to infinity Sn minus limit n tends to infinity Sn minus 1. As just now we understood, both the limits are same. If you replace the limits by their limit values here, L minus L, you will get it as directly 0. Right? When the series is convergent, obviously we'll get the limit of nth term. Understand the difference here. We are not taking the limit of Sn. Here this is Sn, as you can see. This is Sn. This is the sequence of, sum of first n terms, but here it is only nth term. Right? They are not same. Here this is sequence of partial sums, sum of first n terms, but here it is only nth term of the series, right? See, for example, if you have a series like this, summation 1 by n square, so Un is directly 1 by n square only. So if you take limit n tends to infinity 1 by n square, it will be 0, right? But one point you need to understand here: when the series is convergent, limit is 0. But what I'm saying, you see, if the limit is 0, corresponding to that, the series may not be convergent, right? I'll show you an example. This is only a necessary condition. When the series is convergent, limit will be 0. But if the limit is 0, we cannot say anything about the convergence of the series, right? But one point we can tell you here: if the limit is not equal to 0 for this part, if the limit is not equal to 0, then certainly the series is not convergent. It is obviously a divergent series only, right? Understand the point? If the series is convergent, limit is 0. But if limit is 0, we cannot say anything about the convergence. That's one idea. But in a case, if the limit is not equal to 0, then certainly what you call the series is divergent, right? So this is the point here. Now I'll take an example where this fails to be convergent. If limit is 0, then where it may not be convergent, right? I'll take that example now. Look at this question. Now see, as we are discussing, what happens when the limit is 0? If the limit of Un as n tends to infinity is 0, does the series of positive terms convergent? Certainly no. But see, let me show you how it is by taking an example. Now let us consider this series, summation 1 by n, right? When you take this particular series, Un will be only 1 by n, right? It is usually summation Un, and therefore you can understand Un is equals to 1 by n. When Un is 1 by n, what happens to the limit? Limit n tends to infinity, Un will be directly 0. As n tends to infinity, obviously, as 1 by infinity approaches to 0 only. But now the question is whether that series summation 1 by n convergent or not, right? I'm just trying to prove that it is divergent and see how it is. In fact, you see, we are in a dilemma where don't know as of now, we don't know whether it is convergent or not, but I'm just assuming that it is convergent, right? Understand this. I'm just assuming the given series summation un is convergent. I mean, summation 1 by n is convergent. What is actually summation 1 by n if you write all the terms from this? If you just expand it for different values of n, if you take, n starts from 1 to infinity here, for n is equals to 1, we'll get first of all 1 by 1 or simply 1. Then for n is equal to 2, it is 1 by 2. Then for 1 is equal to 3, it is 1 by 3 and so on. You can write as many terms as you want. Now, this is the series what you're considering here. So for this series, though we don't know exactly, I'm just assuming for convenience that it is a convergent series. And moreover, I'm also assuming this series converges to one value h, right? As we know, when the series is convergent, we'll say summation un. For example, if it is convergent to some finite value L, then we say this summation value itself is L, wherever it is converging, that value itself is a summation value. That's how, keeping that in mind, if I assume the given series summation 1 by n converges to h, I'll take sum of all these values as h only, right? Sum of all these values as h only, right? Now see what happens here. If you just add these values, we'll get all this as simply h. Now see what I'm trying to do here. I'm just trying to replace 1 by 3, not replacing actually, I'm just trying to add few other values. Some small number I'm adding here. I'm adding a small number to 1 by 3 so that this 1 by 3 becomes 1 by 4. Okay. I'm adding a small value to this 1 by 3 so that 1 by 3 becomes 1 by 4. Then similarly, I'm adding a small value to 1 by 5 so that 1 by 5 becomes 1 by 6. Similarly, here also, you see, I'm adding a small value to 1 by 7 so that this becomes 1 by 8. Right? In fact, you see, I can add a negative value because 1 by 4 is lesser than, 1 by 3. So I'm just adding some negative numbers to these positive terms to get, 1 by 4, 1 by 6, and 1 by 8 accordingly. Now see what happens when I add these things. 1 by 2 remains as it is, but when you add these two, 1 by 4 plus 1 by 4, we'll get it as 1 by 2. Then when you add these two, you see, we'll get it as 1 by 3. And here also, we'll get it as 1 by 4. In fact, if you just write all these things, except if you exclude this term 1 plus 1 by 2 here, the remaining, 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, again, you are getting the same series, you'll see. So what is happening here? Again, now this new series, which has, very much similarity, this new series is converging to a new value h plus half. You are getting a new value additionally half here. But see, we have discussed it already. When you add some finite number of values to the series, that should not affect the convergence of the series, isn't it? But here what is happening? Just by adding few number of terms, you are getting a new value here. The limit itself is changing, right? This is not true, right? When it was convergent earlier, even after addition of certain terms, you must get the same h. Then only the series is convergent. But when you are getting h plus half something else, how can you say that is convergent? You are getting something wrong here. When this is wrong, you can understand you have assumed something at the earliest, right? Initially, to begin this proof, you have just assumed this, and whatever the assumption you have considered here, that assumption is wrong, right? What is the assumption here? We have assumed that the series is convergent. The series is convergent. So this assumption itself is not correct here. Therefore, since that assumption is not correct, we can say that series is divergent, right? So this is a proof by contradiction. We'll just take a wrong statement initially and we prove that it is wrong, and thereby we accept the other statement. Anyway, since this assumption is not correct here, therefore you can say this series summation 1 by n is a divergent series, right? What happened here? You see, though the limit of nth term as n tends to infinity is 0, we have just observed, the series is not a convergent series, right? So this is one simple example to say, that was not a sufficient condition, right? When the limit of nth term is 0, then the given series may not be convergent always. See, this is only one example. There may be a few other examples which gives you a convergent series, but we cannot generalize that statement. When the limit is 0, then we cannot say certainly the series is convergent, right? So this is the basic idea. And to understand one simple point here, you should not forget, because we use this statement quite frequently. When the series summation un is convergent, when the series summation un is convergent, then this implies limit n tends to infinity un is 0, right? When the series is convergent, then definitely limit is 0. But if limit is 0, limit n tends to infinity un is 0, then the series may not be convergent. You need to just remember this statement, and along with that, the most important point you should remember, in case if the limit is not equals to 0, then certainly summation un is divergent. Okay, so here we are about to now test the convergence of different series, and we are particularly discussing about positive term series. And in these positive term series, so this is what happens when the series is convergent. Okay, now let me just get into how to verify convergence of a given series. Okay, let me just move into this, and we have certain difficulties before getting into this. When you are given a positive term series, and in fact, as we have already discussed, when you are given a series, normally what we do, we just consider a sequence of partial sums, right? By evaluating the limit of sequence of partial sums, we'll just identify whether the given sequence and of course given series is convergent or not, right? If the sequence of partial sums is convergent, then then its corresponding series is also convergent. But you see, in practice, it will be difficult to find some of first n terms in many cases, right? As you know, for example, if I take one simple sequence here, let us say if this is a series, summation square root of n square plus 1 minus square root of n minus 1. If this is a series you are given, right? We need to identify, for example, whether this series is convergent or not. What can we do? We need to take a sequence of partial sums. We need to take what is the first term, then what is the second term, what is the third term. We need to add first n terms from this series. And then we need to calculate the limit of that sequence, limit of the 10th partial sum. But you see here, calculating what you call partial sum, nth partial sum itself is very difficult in this case, right? Not only this, I took a simple example, but in many cases, calculating nth partial sum is highly difficult. So then what can we do? So it is necessary to devise certain methods by which we can decide the convergence or divergence of a series without finding the partial sums, right? When you have a difficulty with the partial sums, obviously, if you can decide convergence or divergence of a series without evaluating the partial sum, obviously it is excellent, right? So we need to think of such techniques where there is no need of evaluating partial sums, right? So in fact, we are going to discuss those methods only now. When you are given a positive term series, you have different techniques we have different techniques in our syllabus, which gives us directly whether the given series is convergent or divergent without evaluating what you call partial sums, right? So among all those methods, the first thing what we are going to discuss is comparison test. In fact, you see, comparison test is a very standard technique which is used in studying the convergence of positive term series particularly, right? So in positive term series, we use this as the basic technique. And you see what we do in comparison test. Let us say you are given one series summation un. To identify whether this series is convergent or not, we'll select one series which is already known to you. Known in the sense it is not a friend or something else to you, but we know the convergence of this series already, right? You are considering one series summation vn whose convergence is already known to you. By considering such a sequence, we'll compare this sequence, that series, with the given series, right? Then by comparing these two, we'll give a conclusion about this series summation un, right? And whatever the series you are considering, whatever the known series you are considering here, we call this known series as auxiliary series, right? I'll tell you how to compare summation un and summation un. That's a different story. But I'm only telling you what we do in comparison tests. So to identify the convergence of this series, we'll use the convergence of known series. When you know already the convergence of this series, this idea can be used in finding the convergence of other series. Let me just get into that. But simply understand one simple point. In comparison tests, always we need one auxiliary series, right? What is auxiliary series? Auxiliary series is a series whose convergence is already known to you. But sir, that is the question. That is it. That itself is the question. No, how can we decide whether that is convergent or not? There are few standard ideas. Look at this. These two are two standard series which are used most commonly in comparison tests, right? There are few simple, elegant, what you call series whose convergence can be identified quite easily. If you look at the first one, it is a geometric series. Anyway, we have considered a series of positive terms here, right? When you consider a series of positive terms like this, a plus ar plus ar square and so on, here you see a is a common term, you can just take it common from all the terms. Even in that case, you'll get it like this: a into 1 plus r square plus r cube and so on. Right? We had seen this already. This is clearly a geometric series with common ratio r. As we know already, this series is convergent when modulus of r is less than 1. Isn't it? It is convergent when mod r is less than 1. But here, since we are considering only positive terms, we may not get, any r as less than 1. I mean, negative. We may not get any r as less than 0. That's how here you see, we are saying this geometric series is convergent if r is simply less than 1. I'm not even considering the modulus, right? Anyway, r is greater than 0 because all these are positive terms. So in case if r lies in between 0 and 1, we'll say that series is convergent. Okay, that's one point. Then the second one, you see, this series is divergent if r is greater than or equals to 1. Okay, this geometric series, it is convergent when r is less than 1, and it is divergent when r is greater than or equal to 1. That is a known thing to you. You have been practicing this since your school, right? Probably at least from intermediate. Then the second series, what we consider very frequently in comparison test is this P series test. Before that, you see, if you recall your harmonic progression, what have you know? This one, 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. I hope you remember this. This is all, what you call harmonic progression, right? This is 1 by 2 is the second term in this progression. Then 1 by 3 is the third term. 1 by 4 is the fourth term. Already know all these things. In fact, you see, these two are quite similar. If you take P is equals to 1 in this, we'll get this particular harmonic progression, right? Remember, in general, we call this, though I'm calling it as a P series, it is actually a harmonic series of order P, harmonic progression of order P. And this, whatever I've written here, the harmonic progression, whatever you have studied earlier when you were in school, that is a harmonic series or harmonic progression of order 1, right? Anyway, this is a P series as far as our course is concerned. P series, and we can write it as summation n is equals to 1 to infinity 1 by n to the power of p. And just consider this directly, though a proof is available, we are not discussing that. This series, this P series summation 1 by n power p is convergent when p is greater than 1. It is convergent when p is greater than 1. And it is a divergent series if p is less than or equals to 1. Right? Just try to remember these two, standard series, and we use these series while, comparing other series in comparison tests. We'll consider either of these two as auxiliary series, especially while discussing about comparison tests. Okay. So when it is summation 1 by n power p, remember if p is greater than 1, it is a convergent series. And if p is less than or equals to 1, it is what you call a divergent series. Okay, so keep that idea in mind. Now let me just get into what are actually comparison tests. See, I didn't actually tell you what are comparison tests till now. I'm only giving you what we do normally in convergence, I mean comparison tests, and then what are possibilities to consider as auxiliary series. So these two are the possibilities to consider as what you call auxiliary series in many of the cases. Now let me just move on to uh, what we do actually, what exactly we do mathematically while performing comparison tests. Understand, you are given you are given one series, let us say summation un, for which you are just trying to find out the convergence, maybe convergent or divergent, whatever it may be. So while choosing auxiliary series, though we have two options now, right? We need to choose one of them. But how we choose that? For choosing the auxiliary series, we need to first write the nth term un in the form of function of 1 by n. Then we decide vn. Understand it by this example. In case if un is given as this, let us say if this is the function un and the series is anyway summation un. So you wanted to test the convergence of this series. Okay. What he is suggesting here, when you are trying to find out the summation of this series, right, sum of this series, to find out the convergence of that series, we need to select an auxiliary series by writing this un in the form of function of 1 by n. In simple, to get a function of 1 by n here, we need to take the highest degree common from this term, of course from both numerator as well as the denominator. So when you take this, what happens, you see, if you take n square, which is in the numerator, if you take n square common from the numerator, we'll get it as 1 plus 1 by n square. And in the denominator, if you take the highest degree term, it is n cube. So that we'll get it as 1 plus 4 by n cube. So you can cancel one n square here, you see. So that we'll get it as 1 by n into 1 plus 1 by n square divided by 1 plus 4 by n square. Now see, whatever the function you have in brackets, all this, I am taking all this as a function of 1 by n. Though I am writing it as function of 1 by n, you can understand it may be a function of 1 by n square or n cube. Not a problem. The idea there is when you take limit, when n tends to infinity, this goes to 0. That is the basic idea. And whatever the coefficient you got here, you see, when you write it as a function of 1 by n, you will get some coefficient here, right? That coefficient is Vn for us, right? While choosing auxiliary series, we just follow this idea in many of the cases. Okay. But anyway, I'll just come to this again. Look at this way. What are actually comparison tests, right? So we discussed, we understood a few points already now. One is the first test to identify the convergence of a given series is comparison test. And in comparison test, we need to choose one known series as auxiliary series. And for choosing auxiliary series, we have two options. One is convergent series, geometric series, and the second one is what you call P series. Now, let us get into actually what are comparison tests. Now, see, there are again two options. The first one is this. When you are given two series, let us say summation un and summation vn, you can understand these two are again positive term series only. When you are given two positive term series like this, summation un and summation vn, and if these two follow this particular condition, un is less than or equals to c into vn, right? Understand, one series is completely lesser than some constant times the other one. For each n, un is completely less than or equal to c times vn. That c may be 1 also sometimes. Okay, that is also possible. Now, when this follows, what it says, you see, summation un is convergent if summation vn is convergent. Here, if summation vn is already known to you, and if that sequence, series summation un and summation vn, if they follow this particular condition, then we say summation un is convergent if summation vn is also, if summation vn is convergent. Understand what it is. You are given it this way. un is less than or equal to c into vn, right? Understand, un is completely a smaller series compared to vn. In particular, if I take c is equal to 1, you can understand it very easily. if the condition is this, un is completely less than or equal to vn. For every n, un is completely lesser than vn, right? Understand it this way. Here vn is the larger one, vn is higher compared to un. When vn itself is convergent, right? When a higher value itself is convergent, definitely its lower value will also be convergent only, రైట్? అక్కడ మనకి ఏం అర్థమవుతుంది, మనకంటే పెద్దవాళ్ళే కన్వర్జ్ అవుతున్నారు అక్కడికి, ఒక పర్టికులర్ ఫైనైట్ వాల్యూకి వెళ్తుంది, మనకంటే పెద్ద సిరీసే ఒక ఫైనైట్ వాల్యూకి మూవ్ అవుతుంది. అట్లాంటప్పుడు దానికంటే చిన్నగా ఉండేటువంటివన్నీ ఫైనైట్ వాల్యూకి మూవ్ అవ్వా, డెఫినెట్గా ఫైనైట్ వాల్యూకి మూవ్ అవుతాయి. దట్స్ హౌ యు ఆర్ సేయింగ్ వెన్ సమ్మేషన్ విఎన్ ఈస్ కన్వర్జెంట్, definitely summation un is also convergent. But it is when un is less than or equal to vn. Always we are looking for this higher value here, you see, right? We are looking for higher value here. If the higher value is convergent, then obviously the lower value is also convergent, right? In other way, in case if un is greater than or equals to c into vn, for every n, for every natural number, if un is greater than or equal to c times v of n, in particular, let me take it as c is equal to 1. What is there? No problem. If for every n, un is greater than or equal to vn for everything, then what happens here, you see? Now again, you see, I'm considering the higher series. Now this time higher series is un. In case if un itself is divergent, right? So I'm now, this time I'm considering what you call the lower series, right? We are speaking about the divergence now. So I'm considering again the lower series vn. If now vn itself is divergent, right? Now you can think of when a smaller series itself is divergent, what can you say about the higher series? When a smaller series itself is approaching to infinity, then obviously its higher series will also go towards infinity only. That's how when a smaller series is summation vn is divergent, then obviously you can say summation un is also divergent, right? So when it is this way, always you know what we are doing, we are considering a series summation vn which is an auxiliary series whose convergence is already known to you. We know already this is whether that is convergent or not. Now you are comparing this summation vn with summation un. See what you have done in the first case, if un is less than or equal to vn, and if summation vn is convergent, then summation un is convergent, right? Un less than or equals to c times v into n of vn అయినప్పుడు summation vn convergent అయితే summation un కూడా convergent అవుతుంది. ఇట్లా కాదు సార్, ఇంకొక రకంగా ఉంది అది. ఎట్లా ఉంది? సమ్మేషన్ un is greater than or equal to c into vn ఉంది, అంటే un greater than vn ఉంది. అట్లాంటప్పుడు vn కనుక డైవర్జెంట్ అయితే అప్పుడు un కూడా డైవర్జెంట్ అవుతుంది. లెస్సర్ ఉంటే vn కన్వర్జెంట్ అయితే un కన్వర్జెంట్. ఇక్కడ గ్రేటర్ దాన్ ఉన్నప్పుడు vn డైవర్జెంట్ అయితే కూడా un డైవర్జెంట్ అవుతుంది. ఇక్కడ డౌట్ వస్తుంది న్యాచురల్ గా, ఇది లెస్ ఉంది సార్ కానీ vn డైవర్జెంట్ అయింది, అప్పుడు నేను దీన్ని వాడలేను, రైట్? See, in a case if un is less than or equal to c into vn, but if summation vn is divergent, when a larger series is divergent, we cannot conclude a smaller series is also divergent, right? In such a case, this comparison test is not applicable. We need to look at other tests, right? So there are different techniques which we are going to discuss, but this test can be applied only when summation when un is completely less than or equals to c into vn and vn is convergent, or un is greater than or equal to c into vn and summation vn is also divergent. In those two cases only we can apply this comparison test, and in other cases we have other methods also. We cannot solve every method by every we cannot solve every problem by every method anyway, but this is one simple idea. And the second one, you see the interesting one, the limit form, right? Now understand, when you are given two series of positive terms, summation un and summation vn, when you are given two series of this kind, see what we are doing here, we are just defining a limit n tends to infinity un by vn, right? By defining a limit of limit of this kind, if you evaluate this, and if that limit is a finite value which is not equal to 0, I don't want this to be 0, remember, I don't want the limit to be 0 here, right? When the limit is 0, what happens, you see, either un approaches to 0 or vn approaches to 0. I mean vn approaches to infinity. They are going in two different directions. One is a convergent series, other one is a divergent series. That's how We cannot speak anything about un and vn here. That's why you see we are not simply considering 0 as the limit, but we are just considering all other values, right? When the limit of this ratio is a finite value other than 0, then we are saying both un and vn behave alike. What do you mean by that? If if this limit is a finite value, if this limit is a finite value, and if we for example, summation vn is a convergent series. If vn is convergent, then un is also convergent. If vn is divergent, then un is also divergent. They behave very much similarly. Okay, so these two are what you call comparison tests, and on which now we are going to do some problems. Anyway, we'll do those problems in the next class.